Yeah, thank you. Thank you. Good morning, everybody. And this is our 12th lecture in the series for cloud physics. And today we have a renowned expert, Dr. Jiwen Fan. Thank you. Yeah. Good morning, everybody, and this is our thank you. Good morning, everybody, and this is our today we have renowned series for cloud physics. And today we have a renowned expert, Dr. Jiwen. Yeah. Why it is resonating so much? Can you?
I think somebody is not mute.
Some issues there. Sorry.
It has been echoing.
Hello. Yeah. Sorry that there is somebody has YouTube on. Can you please switch off? Yeah. Sorry, we have that disturbance. I'm really sorry about that. And today we have Dr. Hello, is it okay now? Okay, sorry about that. There, I think somewhere it was YouTube was on. Today we have Dr. Jiwen Fan from Pacific National Laboratory, and she will be talking about understanding and modeling of aerosol impacts on convective clouds and precipitation. I would request Dr. Gayatri Kulkarni to introduce her.
Audible now? Am I audible? Yes. Okay. So it is my great pleasure to introduce today's speaker. She is a laboratory fellow at Pacific Northwest National Laboratory. She received her PhD degree in 2007 from Texas A&M University, and she is a recognized expert in the field of aerosol cloud interaction, who has made significant contribution to provide better understanding of complex processes associated with aerosol interaction with convection and cloud microphysics. Her work has advanced the fundamental mechanisms for aerosol impacts on deep convective storms, precipitation, and climate. Over the years, she has developed or improved several modeling tools aiming at better prediction of weather and climate for improving scientific understanding. She has played a leading role in cloud microphysics, development of models ranging from very fine scale simulation to coarse resolution climate models, and currently she leads the development of a new cloud microphysics scheme. She has published over 100 peer-reviewed publications, including the high-impact journals such as Science, Nature Geoscience, Nature Communications, and Proceedings of National Academy of Sciences. Okay, so I Dr. Fan to give a talk and share some insight on this topic. Thank you.
Thank you, Gayatri. So I suppose I can go ahead to present.
Yeah, you are audible now. Thank you.
Okay, great. Thank you, Tara, for the invitation to give this lecture. So I'm going to talk about the understanding and the modeling aerosol impact on convective clouds and the precipitation. So aerosol can impact clouds, precipitation, extreme weather through two pathways: aerosol radiation interaction, ARI. This through change the boundary conditions and the surface meteorology because of the radiative effect, and feedback to meteorology, which also will change cloud properties. And then the second way is aerosol cloud interactions, ACI. This is through directly CD cloud droplets and ice crystals. As you can see here, we may change the cloudiness and precipitation and feedback to meteorology and radiation. So the significant scientific problem is that the aerosol cloud interactions, the first thing remains the largest uncertainty among all anthropogenic radiative forcing. So this is the latest IPCC report AR6. As you can see, the aerosol cloud interaction still the largest and cause the largest uncertainty in prediction of our climate. So keep in mind, the IPCC report, a lot of studies are based on the climate models. The global climate models, the aerosol cloud interaction with the cumulus cloud is not considered. So I would say, after at the global cloud reserve scale, so a lot of those aerosol impact through deep convective clouds can be resolved, and those uncertainty can be reduced by then. Now I'll talk about convection. So convection basically is about vertical ascent of the air from the lower to middle and upper atmosphere. So then, because of this, it forms all kinds of convective clouds, such as cumulonimbus and thunderstorms, tube cells, squall lines. There are many other forms. So those clouds, they affecting the radiation balance. They're also affecting hydrologic cycle, energy cycle, circulation, as well as weather hazards. Those weather hazards such as hail, tornado, flash flooding, they can cause life and economic losses. So the convective clouds generally have complex cloud dynamics. So the object of the speed is usually determined by the vertical pressure perturbation and the buoyancy. And the buoyancy term has three factors in there. First is due to the potential temperature perturbation. This is usually what called thermobuoyancy, and then water vapor buoyancy. And then there's a condensation loading, which is a compensate, not fully compensate, partially could compensate the other positive terms. So the vertical pressure perturbation and buoyancy can be affected by various processes at various scale, like the temporal scale, spatial scales in the atmosphere. Therefore, we have very complicated cloud dynamics for associated with deep convection. Well, for cloud microphysics, it's also the most complicated among the cloud types, because it crosses through one phase, mixed phase to S phase. So we have a lot of phase transition processes, also other processes, and we know that there is a poor understanding about the mixed phase cloud and S phase cloud processes. So the phase transition processes here, the orange color means the heaty, latent heaty. So condensation, deposition, ramming, freezing, those can release latent heat. Then we also have the latent cooling process, which is evaporation, sublimation, melting. Well, for the precipitation, this is also the most complicated because we have warm rain, which is through creational growth of the droplets. Well, we have melted rain because of the below the melting level. There's the ice particles can melted from melted rain. Then we also have ice particles can reach to the ground and form as slow drop on hail. So in terms of aerosol cloud interaction, we know that supersaturation is the key, right? Because it determines how many aerosol particles can be activated. So the supersaturation equation for the water phase can be read in this form when we're assuming non-precipitated adiabatic pulsar. So the change of the supersaturation is a function of the vertical velocity and also the condensation. The synctal is condensation. But there's a few approximations people usually use in the model. So the quasi-equilibrium, which means the supersaturation change with the time is approach to zero, which means supersaturation does not change with the time. Then we have zero in the right side. Then you can see the condensation only depends on vertical velocity, not droplet properties. So supposedly we know that condensation depends on the droplet number and the integrated surface area. But with this assumption, you can see that only depend on vertical velocity, which is exclude aerosol impact on the condensation. So in the Razi Poisson, the temperature change also can write down as the Poisson change with the height. So with this form, we can rewrite the equation 1 into the changes with the height. So at the particular height, if this is 0, which means it's assumption of saturation adjustment, then you can see this term so only depends on how hot the Poisson rise, which is adiabatic condensation. Then the condensation also does not depend on droplet properties. So both options is not what we wanted when we do aerosol impact, particularly for convective clouds. So aerosol cloud interaction requires exact solution of supersaturation if we want to accurately simulate them. So in the exact solution, we know that condensation depends on the droplet number and the integrated surface area, which is this equation. And then through integration and also simplification, you can get the condensation rate is dependent on the droplet number and the mean droplet size. And then from Pinsky 2013, this figure from Pinsky's 2013 paper, you can see that so let me explain this lens first. So the gray lens is a numerical model solution, and black lens is exact solution, the equation from the Pinsky 2013. And then there's this dashed line here is the quasi-equilibrium assumption. The dotted line basically is the supersaturation adjustment assumption. So you can see when the pulse rises from 500 meter to 650 meter, you already see there's those different solutions give very different supersaturation. And then when only when it's about this for 5 meter per second pulsar, it takes 30 seconds to reach here. It's close, right? The equilibrium supersaturation is close to exact solution. Basically, a lot of, yeah, but until here, probably they are pretty similar. So this takes like 40 seconds, 30 or 40 seconds. So during this period, there's a lot of changes, processes happening. But if you use different, approximation, supersaturation approximation, then you'll get a different answer. So here is a 3D model for the Amazon case based on the spectrum beam model simulations. You can see here clearly the phase relaxation time, which means the time to reach the equilibrium supersaturation. When we have very clean condition, which is in the updrafts, in the very clean conditions, in the updrafts, the droplet number can be depleted a lot. So that's why you can have very low droplet number. So this requires kind of the phase relaxation time is like 30 seconds. Then when you increase the droplet number, of course, the phase relaxation time will be reduced because the condensation will be fast. Then this is for the one cloud stage. You can see the supersaturation, which is the true supersaturation. The mod is the red, and then the equilibrium supersaturation is in black. And then from the clean to polluted, which is from the dashed to the solid. So as you can see, at either this is a clean condition, which will have high supersaturation, and the polluted condition will have low supersaturation. But you can see, even at the one cloud stage, the true supersaturation is not equal the quasi-equilibrium supersaturation, which means the phase relaxation time is longer. We cannot achieve the quasi-equilibrium supersaturation within the time step we used. So at the deep cloud stage, you can see the differences is much larger. So this shows that indeed, we want to use the accurate solution of supersaturation when we're doing the aerosol cloud interaction to allow aerosol impact on to allow droplet impact on the condensation. So here is showing, which in our recent study shows that when we repress the saturation adjustment in the two-moment Morrison scheme, we actually be able to improve model simulations and also the aerosol effect. So this is the Houston case. This is a thunderstorm in the Houston. This is also part of Pulley tracer activity, ACPC intercomparison study. So we have this single cell around Houston, and the spectrum beam model simulated this cell pretty well. And while the Morrison scheme you can see it simulated a few weak cells. But when we switch to the predicted supersaturation for condensation and the evaporation, then we actually got a better simulation of the cell. And also at the same time, you can see the Aerosol impact. So on the right, on the left, it is the spectrum beam model simulated Aerosol impact on the updraft velocity from the clean to polluted condition. So as you can see, so the original model Merson tumor skin, which is blue, we simulated very small effect. And also the condensation, you can see the condensation, it's just slightly increased, there's not much effect. However, when you look at the golden lines, which is for the predicted supersaturation for condensation evaporation, and you can see the increase, the from dashed to the solid, it's almost similar as a spectrum beam model. The results very similar as a spectrum beam model. This is because the condensation is also very similar. So the condensation is increased significantly with this predicted supersaturation. So this is actually, from this case, we can see, oh, it's promising if we change the tumor model box skin, which is computational chip, and that is good for the ensemble runs and long-term simulations. That could be a promising way just by change this one. But this is just to show how the importance to change it to the predicted supersaturation. Now I'm going to talk about the mechanisms for aerosol cloud interaction on the deep convective clouds. So there's a few mechanisms. I'll start from the wall phase invigoration, which is we also previously called warm phase invigoration. So this one is mainly because the enhanced condensation, as I just mentioned, the supersaturation will be much reduced, but you can see the supersaturation will be very high inside the cloud in the clean case, because the droplet number can be depleted very quickly. So when you added additional like a CCN, particularly here is about ultrafine particles, it will condensation will be much enhanced, and the supersaturation is much lower in the polluted condition. So this effect, is manifested by the ultrafine particles, as I just mentioned. The red parts means the ultrafine particles, which are the particles smaller than 50 or 60 nanometer. And we already showed that this effect is very significant in the Amazon, which is our 2018 paper, and then in Houston, our 2020 paper. And then in tropical ocean, there's a few people already showed those in those regions. So I will use a video to illustrate this mechanism more clearly next. So in the Amazon lower atmosphere, the aerosol particles are low in number but large in size. So those particles, they are activated at the cloud base, and then they rise, and then collide and form rain quickly. So this depleted droplet surface area, and then leaving a highly supersaturated area in cloud. So then with the aerosol particles, small particles from the Manaus plume, which is a big industry city, they produce lots of small particles. Those small particles, they cannot be activated until they reach this high supersaturated area, and they are activated from a large number of droplets. And the condensation of these droplets was invigorated the clouds. Then after the invigoration, and there's more supercooled liquid, and which leads to stronger mixed phase processes for more global layering and rain. So that then the second mechanism, which is the phase invigoration, and this one mainly induced by the enhanced droplet freezing. So from the this is a schematic figure in Roosevelt 2008. You can see in the polluted condition, when we have lots of CCN activated at the cloud base, then the warring will be suppressed significantly. So this will allow a lot of droplets being transported to above the freeze level, and then have a much larger amount of supercooled liquid, and freeze of this extra amount of supercooled liquid would enhance the convection. At the same time, also because we have more precipitation, and the precipitation will offloading this will allow more significant effect from latent heat. So this effect, we do see the loading effect. There's some extent of loading compensation, but I want to note that the freezing itself does not increase loading, because it doesn't change mass when you change, freeze it from liquid to ice. And the latent heat from freezing actually is very small. But the most important part is the follow-on growth after freezing. This is mainly usually through deposition and then ramming. They increase latent heat a lot. They also increase condensation loading. So, however, in many of our models, our studies, we showed that the buoyancy increase is only partially compensated by the decrease from the increase of loading. So this is shown in many of the studies, which you can read more from the studies. And then, because also usually in those type of clouds, we form global and hail, like slow global hail, they precipitate out, and that offloading allows the latent heat effect being more significant. So we do see those effects plays a role in some cases, but our recent sensitivity tests showing that generally the warm phase invigoration plays more significant roles compared to the ice phase invigoration. So here I want to show in the Houston case what we see. So you can see this in the mixed phase stage, we already see significant aerosol impact, which is from the dashed, from the dotted to the solid line. And this effect basically is because of latent heating from high level. And low level, we do also have latent heating from condensation. But the high level increase is significant. And we look at the condensation loading. As you can see, condensation loading effect indeed from polluted to clean from clean to polluted is enhanced. And then, however, the semi-buoyancy, which is the red, from clean to polluted is increases more. So the net effect, the total, you can see there's some compensation at around kind of 5 to 7 kilometer, and then in the other places you can see there's an enhancement in the latent heat in the buoyancy. This is the buoyancy. This is in the mixed phase cloud. So when you get to the deep cloud stage, then the aerosol effect is very significant now. So then the changes mainly because of the latent heat from the condensation enhancement. That's because at the deep convection stage, supersaturation larger, and there's more ultrafine particles can be activated. So that's why the ultrafine particles plays more significant role. And you can see now we don't see much compensation. The condensation load can only compensate at around 6 kilometer. So there's the late buoyancy is increased at low level and high level. So this is just to show, we have this. We do see this in the Houston case, which is both cold and warm phase immigration plays a role. So the third mechanism is the through Codepool feedback. So there's a low consistency about how aerosol would impact the Codepool intensity. Some studies shows enhanced Codepool intensity, but some studies showing the weakened Codepool intensity. So we show that it's actually depends on the low-level wind shear condition to see if it's this is particularly for score 9, so the quasi-linear system or score 9 system, because the balance between the Codepool and low-level wind shear is very important. And also Grant and Van de Hever, they showed that if it's enhanced or weakened Codepool depends on where the dry layer is. So here I showed that in both Label Morrison study and our Chen 2020 study, we showed that for the score 9 case, well, the clean case, the Codepool is stronger than the polluted case. So increased aerosol leaded to a weakened Codepool. But this weakened Codepool actually leads to stronger convection because it's better balanced with the low-level wind shear. So previously, Codepool is too strong. So it's not optimal balance. And now with weakened Codepool, now the Codepool is better balanced with the lower wind shear, lead to more upright updrafts. So this invigorated the convection. So here is a nice study I just mentioned from Grant and Van de Hever. You can see they put different put dry layers at different levels. So the black line is the moisture profile, this low significant dry layer. This is a control run. And then the purple line, which is the dry layer mainly located at 2 to 3 kilometers, which is close to cloud base. And the cyan line is for dry layer mainly at 3 to 4 kilometers. So this is for precipitation as a function of time, and Codepool intensity and updraft speed, which is updraft error, not just speed error with the updraft larger than 5 meters per second. So you can see clearly when the dry layer is near the cloud base, which is for the purple line. So increase aerosol, the solid line is the lowest aerosol, and then increase from the dashed to dashed and dotted line. So you can see there's an increase of precipitation, and then you can see also there's much enhanced Codepool. So because this is the temperature, the minimum potential temperature, if it's more negative, which means more stronger. So you can see that the Codepool gets stronger, and so the updraft speed also gets larger. So this means increased aerosol needs stronger Codepool and then larger convection and precipitation. And this is because this we have a stronger cloud droplet evaporation if we have a dry layer over there. But if the dry layer is higher above cloud base, which is 3 to 4 kilometers, and then you can see we have opposite result. So the coupole is weakened. It's then this is well reduced supersaturation and also the convection and the supersaturation. This is mainly because reduced droplet evaporation rate. Raindrop evaporation rate. If you have the because it's too high, the dry layer is too high. So in the lower level, it's humid. That's why we have a reduced droplet evaporation rate. Now, the fourth mechanism, which is also through feedback. This is recently people talked about a lot. So this is through moistening the environment. So because of the enhanced drop evaporation in the polluted environment, that can increase the environment humidity, and this can lead to a large scale convergence and convection. And this is showing in the Abbott Chlorine 2021 paper. You can see this is a huge increase and also huge increase in the water vapor. It's more than 1 kilogram per kilogram. This is really large. And then the evaporation in enhancement is very large. So this effect, we know that it's exaggerated in this study because there's a couple of reasons. So the first one, okay. First of all, I'll show the most recent study. This is mainly from Danny with his students, and also I'm involved. And we show that you can see, this is also our trial because our analysis showing that specific humidity and also relative humidity. The dashed line is from the Abbott Chlorine 2021. So I use AC 2021. So you can see much larger than the observation, the satellite analysis we did. And then the relative humidity also huge. So this is already shown, and this paper is in review, and it already shows that we actually use some way to separate the feedback effect and showing the feedback effect. It's just there's some effect, but it will not be that significant. So then from the modeling perspective, so this is also recent study from Dagen, and also in review in communications, earth and environment. And you can see that they show that it's because of the different boundary conditions can be cause a large this large effect. So the blue line, which is from AC 2021, from the WTG experiment, and then RCE experiment is a solid line, and all the other lines from different literature studies. You can see how big it is compared the realistic simulation with open natural boundary conditions. So RCE is the idealized condition, and then the WTG, both of they have the periodic natural boundary conditions. So with the periodic natural boundary conditions, also we know that the domain size only have 100 kilometers, something like that. So you can see the domain keep humidified is unrealistically here moistened. And also they're set up another setup besides the idealized periodic lateral boundary conditions. They also set up, for example, fixed droplet number and also saturation adjustment for condensation vibration. Those are the things that we are trying to avoid for doing aerosol cloud interaction. So both of these factors can lead to overestimation of droplet in vibration. This is already shown in quite a bit of previous work. So those are the but we do need to keep in mind that this may be another mechanism we want to consider. So besides the aerosol impact on the convection, and then here I'm talking about the aerosol impact on the cloud cover, cloud thickness. So the most significant effect is that we found that the CCN can increase the even cloud cover and cloud thickness. So this study, which is based on the motivation was mainly because a lot of observations already showed that, such as those observations already showed this, and then we want to use the model to simulate it. So we simulated this over the 3 locations. At each location, we had 1 month simulation, use spectrum beam model. So the 3 locations are the TWP region, and which is a tropical warm pole, SGP, South Great Plains, and the southeast of China. So this is more like a statistic to see more statistics results. So we found the similar results as observations. We're also trying to find the mechanism. So the dominant mechanism is because the macrophysical effect of aerosol, not the invigoration. So how it works? So first of all, in the polluted condition, you have suppressed warm rain. This will allow much more cloud mass being transported to high level, detrained into the stratiform amber region. So this detrainment mass is much larger. And more importantly, is because of this ice particles. The detrained ice particles are much smaller compared to in the clean conditions. So this leads to much reduced force speed of ice particles. So in the updrafts, these particles will not fall. Because they are balanced with the updrafts here. This leads to much slower dissipation of the clouds. So the stratiform even or you'll see much larger cloud cover and thick cloud. So this is this effect now has been also simulated by many studies. So it's pretty much important effect because it has a strong radiative effect. So you can see here is that overall we see a light cooling in the TOA and surface, but in the atmosphere we see warming. But when you break down to the nighttime and daytime, then we can see that in the daytime we do have a light cooling effect, but in the nighttime we have a warming effect. So that is showing that this will reduce the diurnal cycle temperature differences. So this was also observed in the recent decades in Indian monsoon region, which is from Saranja's study, 2018 study. It shows that there's a 0.6 degrees Celsius reduction in the diurnal temperature, and which is exactly the number we had actually in our paper. So this warming, particularly at night time and high level, and can it's maybe a very important first component that the climate model missed, because as I mentioned earlier, in the climate model, the aerosol impact in the cumulus cloud in the D trend as the particle properties is not considered. So now here I want to show how about in MCSs, because the mesoscale convective systems, those are huge convective systems. Sometimes they also last for a long time, like even days. So then here we change vertical wind shear. We form different type of MCS cases. This is kind of the mesoscale complex. And then, when we increase low-level wind shear, we got more like quasi-linear system. And then with change the middle-level wind shear, we actually got a supercell-like system. And then, this is for change to the up-level shear, which the overall structure doesn't change much. This is for change the shear, increase the shear through lower to upper atmosphere. So that's actually change convection too much. But those are different systems. What we find that, so when we increase the vertical wind, so when we increase the aerosol, you can see here from clean to polluted, the vertical mass fluxes was enhanced consistently. Of course, in this one, which is a strong wind shear throughout the whole entire atmosphere, then there's not much effect. But the sign still positive. So this is because majority is because of condensation heat induced invigoration. However, for this case, for the linear system case, we do see stronger low-level convergence, and because of the Codepool change, like I mentioned earlier. So the Codepool was weakened and better balanced with the low-level wind shear. So this is a strong low-level convergence. We also look at the cloud region change, and similarly, we see what I just showed, the aerosol macrophysical effect, which is reduced the cloud fraction in the lower level. So the shallow cloud was reduced. So this is cloud thickness, and this is the cloud top height. And you can see this is the shallow cloud. They are reduced because this is the number here is the negative. And while when you look at the deep convective cloud, this is usually the convective core, because it has a high thickness, very large thickness, and very high cloud top height. So they also generally enhanced. Many, they not that significant, of course. This case is more significant, but the stratophone and cover, which is this part cloud, they are usually increased along here, and those lines, they are usually increased. So we do see that the same thing, which is a similar mechanism. So stratum and cover was enhanced, and the reduced shallow cloud, which is mainly we assuming that because you have a larger cover, that's will reduce the surface fluxes. We do see that reduced the surface fluxes, then that will affect shallow cloud much more. Okay, so now about this convective stratiform precipitation. Particularly stratiform precipitation is very important because in MCSs, this is a cover of very large area, and the stratiform and heat has very important effect on the potential vortex and also the circulation. So we see that because of enhanced vertical mass fluxes, we see convective precipitations are generally increased in all cases, as you can see. And stratified precipitation is also increased, and the increase is much more significant compared with the convective precipitation. So yeah, this is a very important results because stratiform precipitation is responds more significantly to the aerosol. Okay, so many of those studies just a single case, or sometimes we run small ensembles, for example, 3 member or 5 member. So what about if we change the meteorology, perturbed meteorology and aerosol simultaneously? Like how the aerosol effect would look like. So those are the recent studies look at the user ensemble method by perturbing both aerosol and meteorology conditions. And then in this paper, which I also involved, we carry out this large ensemble. We did like 1,200 simulations by very CCN and initial meteorology conditions. And what we found out is that although meteorological perturbation produce large uncertainty in predicting the Sahel and the total precipitation, however, very CCN causes even larger uncertainty. So we also found that the CCN changes the hail and the precipitation predictability significantly. So here is the figure showing the predictability. This is a singular to loss ratio, which is measures predictability. So for the hail precipitation, for the total precipitation, this is for each CCN, we have so many ensembles by change all kinds of meteorology. So this is the ensemble results. And you can see they change CCN from 100 to like 3,000. The total precipitation, the predictability is changed from like 4 to 1. So which is a huge change. So means Aerosol CCN impacted this precipitation predictability a lot. So overall, the higher predictability is low compared to total precipitation, but still, we can see some differences in the higher precipitation by change CCN. Now, I want to mention, I think I probably have a couple minutes. I just quickly mention that. So aerosol cloud interaction often interact with non-atmospheric interaction, which is strong for the urbanized area, because lots of aspergenic aerosols are emitted from this urbanized area cities. So that is something I want to emphasize, because in the past, a lot of studies just consider either just aerosol impact or the non-atmospheric interaction, the Oberkampian model. They do not consider both effects together. So our research in those 2 studies is showing that when they work together, they could have a large nonlinear amplification. So their effect can be larger than either of those effects. So these 2 studies, one is the Houston sea breeze induced convection, and then the other one is Kansas City, which is here. This is a supercell storm case. So I will just use one slide for each case. So this is a temperature. 2-meter temperature differences between the oven case without the oven. You can see also the aerosol considered here. The heating temperature is pretty large here. And the convective storm initiated and happened here at the boundary, urban-rural boundaries. So this because we have stronger moisture and temperature contrast. So secondary circulation happened here. And this is we found that both the non-atmospheric interaction, which is the overland, which changes the sea breeze circulation. So with the overland effect considered, the sea breeze circulation was enhanced a lot, and the aerosol effect is pretty small on the sea breeze circulation. So this you can see the overland effect. This is the differences is compared when we consider overland and between this baseline. You can see we have enhanced the updraft velocity. This is the overland effect, which means when we remove the when we replace the overland with the surrounding cropland, and you can see this is a much larger effect in the lower level, which is impact the shallow clouds, shallow convection a lot. While the aerosol effect generally enhanced the occurrences of this large vertical velocity in the middle and high level through the low to the high level. Sorry, my computer always has this. So you can see when they work together, we see much stronger joint effect on the convective intensity. So this is, I didn't show the precipitation. Basically, the heavy rain rate also has a nonlinear amplification. When they work together, the occurrence of a heavy rain rate was enhanced a lot. So this is for the Kansas City supercell. And this one is because at this Kansas City, also at this northern city area, we see this secondary circulation, which is also caused by the stronger moisture and temperature contrast. This circulation actually, this circulation, well, when they pour the stone, the preformed stone is green to get toward this city. Well, in the low overland case, we don't see any of this circulation. So those convergence does not exist. So this, only 20 minutes later, you can see they meet together. They produce a much larger convection. While the convection also covers the city. So actually, I didn't show after another 20 minutes later, the half of the city was covered. So, but in the low overland case, the storm will just go through the east of the city, does not be close to the city, the location of the city. So the storm path was changed. And this effect, this pull the storm toward the city, allows the more aerosol can interact with the storm, which has a large impact on the hail. So you can see the joint effect has increased the severe hail and the significant severe hail by 19 to 22%. Any individual effect, which is the overland effect and the aerosol effect, particularly for severe hail, their change impact is very small, and this is a very large nonlinear amplification when they work together. So in summary, so I showed that deep convective clouds have complex dynamics and macrophysics. This making very complicated aerosol deep convection interaction. And similarly, aerosol impact on deep convective clouds requires exact solution of the supersaturation. Basically, any clouds I would use the exact solution of supersaturation, but this is a more significant impact on deep convective clouds because the high supersaturation makes a lot of differences. So the quasi-equilibrium and saturation adjustment assumption basically exclude the aerosol impact on the condensation and evaporation that will distort aerosol effect. So we discussed the 4 mechanisms for aerosol for CCN can impact on convection and precipitation. So one is the water phase invigoration due to enhanced condensation. The other one is the ice phase invigoration induced by enhanced droplet freezing, and then through Codepool feedback and also moisturizing feedback. I want to emphasize that aerosol and cloud interaction really depends on the conditions of meteorology. For example, we have this wind chill impact and RH, cape. They all modulate to those mechanisms. So we also have the high supersaturation in the deep convective clouds can activate this ultrafast aerosol particles, which have a very high droplet number concentration in the pollution plume. I think I hear echo. Yeah, so those ultrafast particles, they have a high number that can lead to very drastic aerosol impact. So we also showed the CCN increase cloud ambient cover and thickness because of the reduced ice particle size and the force speed. This may impact the aerosol forcing a lot, but it's not considered in the global models. So I also showed a little bit about aerosol cloud interaction works with the non-atmospheric interaction in the overlapped region. This will lead to a much larger modification to the deep convective clouds and the extreme weather compared with the individual effect. For example, many studies only consider aerosol impact. Some other studies only consider the open non-effect. So this is what I want to emphasize because a lot of aerosols comes from this overlapped region. So many of this are summarized in this book chapter. So this is the aerosol and the climate. This book will be available in March, I think. And this one is meant for textbook. So we had a book chapter there, and this was summarized there. And I hope you will read that book. Finally, I want to acknowledge the DOE for the funding support, and also my postdocs who has my postdocs and visiting scientists who involved the work I presented in this talk, my collaborators. Yeah, thank you.
Thank you.
Happy to ask. Yeah,
Thank you. Thank you,
more...
Jiwen, for a fantastic talk. You touched upon from the very basic aspects that we need to be more vigilant on, and to various aspects that are controlling the aerosol cloud interaction and associated processes. I would maybe we will first go to any questions from anybody who is watching. Sachin?
I think there are no questions on the YouTube at present.
Yeah, we'll take the questions from the person in this team.
So may I ask a question?
Yeah.
Yeah. Jiwen, very nice talk, and I learned many new things about the aerosol cloud interaction and the microphysical effects of aerosols. I have just general two questions. In one of the slides, you showed the effect of this microphysical aerosols on how it increases the envelope cloud cover and the thickness. So I was wondering how it will affect the duration and intensity of the rainfall from stratiform envelope clouds.
Okay, so I think you asked the question about the rainfall for this study, right? Or for this one. This one,
No, the previous one.
Yeah, this one I showed the convective precipitation, stratiform precipitation. You can see both of them are increased. For this one, yeah, the non-total precipitation.
Yeah, so this slide, yeah.
Yes, so this one actually in the supplemental material, we have a figure shows precipitation, which is a lot in the formal paper. That one we look at the total precipitation increase, which is it's like only 5%. So it's pretty mellow. But when we look at the PDF, so the rain-red PDF, we can see a shift. So there's a reduced laddering in the polluted condition, and then there's the enhanced heavy rain. So there's a PDF shift from the there's more heavy rain, there's less laddering. So that is very significant. Also, it's consistent with many observational analysis as well, particularly in China. We had a few this kind of studies showing in China the laddering, particularly in the south of Middle China, the laddering was reduced significantly, and the heavy rain was increased. Yeah, but over the large domain, when you look at the total precipitation, and generally, a lot of times we cannot see a bigger change because convection is so kind of stochastic, right? When we enhance convection in this part, it may be different precipitation or convection in the other part of the domain. So a lot of times, the domain precipitation is kind of balanced by constrained by radiative forcing. The later kind of the periodic boundary force, particularly, you will constrict. But we usually don't use periodic lateral boundary condition. So kind of like I think from 2012, I switched to the kind of like the real case simulation because I do find a significant differences between this idealized periodic boundary condition, which is problematical for convection, because for deep convection, a lot of times there's a it's exchange between the convective region and the surrounding regions. Yeah.
Okay. So there are two questions from the YouTube. I have posted in the Teams chat window. You could see those questions.
Yeah, I can see. I see from Sandeep says,
Yes.
yeah, the Codepool feedback Which process has dominant effect? The shear effect of position. So this is a good question actually. So right now, people are doing, individual studies. A lot put this together. So when we look at for example, Label and Zach Label and us, we look at this. Look at this for the linear system, scroll-down system. So here, you can see they are, the shear. We have weakened. We see weakened Codepool in the blue distribution, and this weakened Codepool can be better balanced by wind shear, because low-level wind shear is not that strong here probably, and the Codepool in the clean conditions is too strong, which actually lead to the tilted convection. So in this type of system, it's basically the balance between cold and shear. But the dry layer, this is a separate study, which is not a score. It's just I think this is for general like isolated convection. So this one, that's why when you see increased Codepool in this dry layer near the core base, you can see increased aerosol need stronger Codepool and enhance precipitation. And the weak Codepool leads to reduced convection precipitation. But in here, we see reduced Codepool leads to the enhanced convection precipitation. So it's really, convective system type is very important. Because there are very different type of convective systems between these two studies. So I think we really need more studies on this aspect, because there's not many studies on this, and the literature study has different different model gives different results. Some people showing the decreased Codepool by the CCN. Some people show the increase. Probably with the same case, use different model of different microgrids. This effect can be. So yeah, good question. Really, more study at least on this aspect. So another one, another question.
Mahen, will you please mute? I think some disturbance is coming from you. Just
This
Another question is when are the strong convections observed over the rural orbit boundaries, daytime or nighttime? Okay, so we actually in the two cases I simulated, which is Houston, which is in the late afternoon, so it's daytime. The convection basically initiated here, and then involved in the afternoon. But in the Kansas City, basically it's real nighttime. It is still daytime. I mean real nighttime. So we do see the temperature differences is still significant. So there's another effect I want to mention is that with the overland, you have a delayed effect, because it's hard to say. Maybe I should not say delayed, but the heating can be persistent through the night. So very often, even at the nighttime, we see this the heating in the urban rural boundaries. The temperature is still much higher, even at the nighttime. So it's extended to the nighttime, and that's why we still see that effect. So for the Kansas City case, it's kind of at nighttime already. Yeah, this is only 6 hour differences. So it is nighttime, but this secondary circulation occurring much in the daytime and then becomes stronger with as time evolves. So at this time, and it's the strongest we see. It starts much earlier, so during the daytime. Yeah, when there's a low convection system, there's nothing there, but this is kind of like a turbulence convection. This convergence, divergence couplets, which usually we call the secondary circulation. Yeah.
There is one more question.
Yeah.
Yes.
See, what is the likelihood for aerosol cloud interaction to happen if there's a low convection? So, you talk about all the type of clouds. So if there's a low clouds, there's of course low aerosol cloud interaction. Because here we're talking about the clouds due to convection. So this is a convective clouds. So when we have convection, and then it's initiated, the condensation, activation, condensation from clouds. So I'm not quite sure if you talk about other type of clouds. For example, cirrus cloud and stratiform clouds. They are through other, for example, stratiform clouds, stratocumulus. They are due to the inversion, and that is a very different aerosol cloud interaction. And the major concern is the radiative effect, because those low-level cloud has a strong radiative impact on the Earth's radiative budget. So I'm not sure if I understand this question.
Yeah, probably it is to that is the answer that they sought regarding the stratiform clouds. Is there anybody else wanting to ask a question to Jiwen?
Yeah, hi, Jiwen. This is Mohen.
Okay, Mohen, please go ahead.
Yeah. Hi. So I want to ask a question. Very nice talk, and it is really informative. So I want to ask about that stratiform effect of CCN on the stratiform cloud. Like you have said, if you are having more CCN, then it will have a deeper anvil, and the ice size size of the ice particles will be smaller with less fall velocity. But if it is deeper, if ultimately it will produce larger raindrops, right? Because they will collect, because it is deeper, it will collect more water vapor, and it will grow, collide and coalesce, and it will grow bigger, right? Ultimately.
Okay, so that is for maybe not for this type of stratiform, because generally from the D trend, the ice particles, there's not much liquid in the stratiform associated with deep convection, because they are at a very high altitude and the temperature is pretty low. So there's not much liquid. There's some ramming, probably, very, small amount of liquid. So that is, so I'm not sure that process can be strong in the stratiform associated with deep convection, because we don't see much liquid in those stratiform and there are many the ice aggregation and produce the slow. So the stratiform precipitation generally it's much lower magnitude. The rain rate much lower magnitude compared the convective region. But because in MCS, those stratiform, why I was emphasized here is because stratiform is a very huge area in the MCS systems, the mesoscale convective systems. So those, if you change the stratiform precipitation lot, because it's large, very large area, and the stratiform latent heating does have a feedback to the circulation. So that part is an open question. I think it's going to feedback to the circulation lot, but because from the modeling, we need a very large domain to do this, and that's actually something I'm very interested to work on next. Yeah, how this feedback to not just get dynamics. Good question.
Any more questions? I also wanted to add there to ask you also more on that. In the stratiform, there can also be embedded convection. So those ones will be of importance for the aerosol cloud interaction as well, right?
Okay. So you'll talk about the stratocumulus,
No, we have in India we have something like the nimbus stratus in the initial stages. Actually, they also have a lot of embedded convection. So eventually, they do produce a lot of rain because they keep on raining for a long time over a wide area. So it's a significant contribution to the overall rain.
Yes. Particularly over monsoon period, right? There's a lot of like a stratiform, large scale. We call that kind of a cloud called a large scale stratiform. So among this large scale stratiform, inside there's convection going on. Yes, that is another type of another type of cloud, and that particularly significant over the monsoon region. Yes, that is something also very interesting to look at how the aerosol would impact the precipitation and the convection precipitation in this type of cloud, because they are pretty large scale as well. Yeah, it's kind of very large, and inside there's a lot of embedded convection going on. Yes.
And is it okay if I ask you a couple of questions? Is it too late for you?
That it's fine. I'm okay. I sleep late.
Yeah. You mentioned about the warm phase invigoration, which is the key even for the ice phase invigoration also. So don't you think that we have to focus on the warm rain processes more vigorously to see? For example, we don't right now the supersaturation, understanding of the supersaturation is the key. But we know we don't observe it. So we know very little about it. Whatever we know is from the model and the theories. What do you really propose? What exactly a cloud physicist should do, or like there are many young people that are listening to the talks. So what do you suggest to them? What they should focus? Actually, what should be their motivation to do this science?
That's a very good question. It is very difficult because in the convective core, we don't have measurements for those, for supersaturation and the updraft speeds. Sometimes now we do the radar people, they use dual Doppler radar or even triple radars to try to get the estimate the updraft speed. So So indeed, this is a very challenging question for the convection, for the cloud, community, particularly cloud macrophysics community. So to me, I feel maybe it's hopeful through the radar measurements to gain more understanding about this cloud macrophysics processes and dynamic semi-dynamics in the convective core. So because if we have this radar, for example, people they use the RHS scan, they can track the cell. So this is what we use in the Houston field campaign, which is called a tracer field campaign. So in the tracer field campaign, we use the radar to track the cell. And there's some strategies that the radar people implemented for that field campaign, which I don't know that much. I also didn't follow, but that is what we will trying to. We have a surveillance radar, and then we have a radar track the cell and measures the. So with dual or triple radar, we can get the estimate voltage velocity, and then the radar signal, the parametric, signals can give us a lot of information about the cloud macrophysics processes. For example, ramming and the melting and those kind of things. Yeah, I hope from the radar, because the aircraft, it's very difficult to it's not safe, right? So maybe by advance the radar activity, radar technologies, this will be hopeful. And particularly to me, I think maybe we should focus more on long-term measurements. For example, Amazon, like Go Amazon here, we only have basically only have the one season of the data analyze this study, because the second season, the second warm season, the Aerosol doesn't change much because it's raining too much. So if we have long-term data there, that can definitely because this is downwind of like this. You can see from this figure, the site is in the remote region, is downwind from the city. So if we have much long-term measurements there, and then we can get statistical robust results to understand this Aerosol effect. So that is one of the ways to quantify this Aerosol effect. So in India, I think the same thing, and China, if we build those in those regions that warm or humid, the Aerosol impact could be very significant. We want to build this long-term measurements. Yeah.
Get and one more question I have is regarding actually you mentioned that the predictability. There was a mention of one work where 1,200 ensembles you have you showed this, where the hail precipitation and total precipitation, you talked about the predictability of the precipitation by including that has enhanced by including the CCN. See, we know that the observations of CCN itself has a lot of like variability. So how do we comprehend these two aspects, that the CCN observations itself is quite variable, and the model, actually we need to have a CCN to increase the predictability. So how do we comprehend these two aspects?
So are you asking in the model
Yeah.
how do we consider the CCN so that the CCN can impact the predictability?
Yeah.
Okay. So in the model, well, we have, for example, a lot of times we need to simulate the aerosol properties. That means you need the chemistry aerosol component in your model so that your model can simulate the aerosol because the aerosol varies a lot, rather especially, particularly when you are in the the land surface is very heterogeneity, and the overland, you have maybe much more aerosols, and then you compare the forest, and then the aerosol number could be much lower, but then the aerosol type also very different. So I would suggest if you simulated a case that aerosol varies a lot over your domain, then you want to use aerosol module, a chemistry aerosol module. For example, we use Wolfgang, right? So Wolfgang, which can simulate this aerosol much better compare if over your domain you use the prescribed aerosol everywhere, that also will affect your simulation a lot because aerosol heterogeneity indeed affect the simulation of the aerosol effect a lot. This already shown in a couple of papers.
Yeah.
So we would like, for me, when I simulated the channel, the case in China, because the aerosol heterogeneity is large, then I usually will include chemistry like Wolfgang coupled with spectrum beam. So all those studies actually those are use Wolfgang coupled with the spectrum beam model. So chemistry is aerosol chemistry, they are explicitly simulated in those cases. There are a lot prescribed, as you can see. So the domain here, you can see this is Houston, right? We have a very high aerosol compared to this ocean.
Exactly.
Yeah, low aerosol, rural area. So that's why I cannot prescribe the aerosol over the entire domain, just use one value, right? So that's why I use Wolfgang coupled with spectrum beam. Yeah.
Yeah. There are two more questions posted in the chat.
Okay, let me see. Okay, so
one from Ali.
Yeah, Ali, it says, wonder how the increased aerosol node affected the frequency of warm and cold fog formation. Yes, that I don't do I don't do fogs, so I probably should not say much about it. But if you do have very large aerosol, as we know that the water content is limited, right? So then if you have too many aerosols, you have very small droplets, and then you will get foggy. It's not a cloud, it's foggy. The droplets, I mean the activated aerosol cannot grow big enough to become droplets. So that's the concept I have. So the other one is saying that meteorology mesoscale system, is there any ACI impact on the synoptic scale? Yeah, so I don't, because we didn't run, the domain is large enough, it's not large enough, and also for each case we only run 1.5 day after the spin up. So this prevents us to look at the feedback to the synaptic scale. So that as I said, this is a very good question. How the aerosol interaction can have an upscale impact to impact the synaptic scale or even large scale circulation. That is a big open question and also a good motivation for students to work on this field.
Yes, yes.
Thank you.
Yeah, let us all thank you, Jiwen, very much. There are more questions, but I think it is quite late for you right now, and everyone feel free to contact her. And it has been very nice. Thank you so much for giving this wonderful talk, and we are really sorry about the initial glitch. Thank you very much and appreciate. Thank you so much.
Thank you.
Thank you.
Yeah.
Thank you. Thank you, Jiwen. Bye.
Yes. Thank you. Bye-bye.
Bye.
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 Padmakar.